Hi everyone. So this video is going to be on section 2.5. It's still on the exact differential equation, but it is an extension of that for the case where the m and n term would have a common factor and you cancel out those factors. So to really understand this section 2.5, we'll start with the solution again. We'll differentiate this and we'll see what will happen. Okay, so here's my solution. All right, so I know that when y is 0, x is 1. Okay, and I'm going to differentiate the left and the right. So let's see what we get. And so the right side's a 0. And I'm just going to jump right into the differential here, the dx and then the dy. So the dx is going to be 3x squared and then the 2x e to the y. And then dy is going to be x to the third plus x squared e to the y. Okay, and you notice something. They all contain a factor of x. So we're just going to assume that x is not 0, divide everything out by x, and you get another different differential equation. And something can happen here. You can actually move this around. So let's say I move this whole thing to the right side. You get that x to the third plus x squared e to the y is equal to the negative of 3x squared y plus 2x e to the y. You move that dx over. Move this guy over by dividing this out. And someone can clean up this differential equation by really canceling out that common factor top and bottom, which is your x. So I can clean up the top by canceling out an x. Cancel the x in the bottom. And now this differential equation is not exact anymore. And that's because I cancel out the common factor. In this case, this guy was exact, but I did a simplification that caused it to not be exact. So how do I retrieve back that x? So this is not exact because I actually divided out the x, right? The same. So I can divide the left side by x, divide the right side by x, and you get another form of this differential equation. And it's not exact. And that's because we're missing that factor of x. So how do I get back that x? And that's exactly what 2.5 is going to explain. So let me explain 2.5 in the general setting, and then we'll go back to this example and retrieve back that x, okay? All right, so we start with the differential equation. And we can't assume that m is f of x. We cannot assume n is f of y. If it is, then it's exact, and we can just go ahead and solve that with the exactness method. We're going to assume that it's not exact, but that there exists what we call an integrating factor. which is that little a common factor that we cancel out. And we can't assume that it's just purely in terms of x or in terms of y. It could be in terms of both x and y, such that if you multiply both the left and right side, so let me write that in blue. So if I multiply the left by u of xy, it will now be exact. So this here is exact. This here is your f of x, and now this is your f of y. Okay. And we're going to check that it's exact, assuming it is exact, which means that f of xy should be equal to f of y x, which means if I take the left side, which is u of xy m, and I differentiate that with respect to y, this is going to be equal to differentiating the right side with respect to x. Now this is a product rule. So here this is going to be, if you apply the product rule to this guy, you'll get du, let's see, du with respect to y, but I'm going to keep the m, plus, I'm going to keep the u, and this is going to be dm dy, and is equal to, this is the product of u and n, so I'm going to differentiate the u with respect to x, keep the n, plus I'm going to keep the u, differentiate the n with respect to x. Okay? And our whole point here is that we're trying to figure out what this u of xy is. There it is, there it is. I'm going to move things around. I'm going to move this over to the right side, move this over to the left side, and solve for this u. So I can do it by moving this to the left. And once I move it over, I'm going to factor this out. So it's dm dy, dn dx, and the right side is going to be du dx times n minus du dy times m. Let me just check to see if I'm doing this correctly. I'm not seeing the next step. All right, so this is correct. This is where we're stuck, okay? This is where the problem lies. So this is not easy to solve. This is a differential equation that if you try to solve u of x, y, you're going to have a hard time. But if you assume the simplest case, it's actually quite easy. So we're going to make it this differential equation to solve for this u of x, y a lot easier. So case 1, if it turns out this u of x, y is simply just in terms of x, okay, it would make this differential equation a lot easier to deal with. So if u of x, y turns out to just be a u of x, which means there's no y involved, it implies then du of y, du of dy to just be 0. Here's du of dy. So this, if this is 0, this whole thing is 0. So then you have u of x dm dy minus dn dx. That's a 0. So this is du dx times n. And it turns out this guy is separable. So here's my du. I'm going to move this u of x over to the right side. And move this dx over to the left side. Divide everything by n. And it's still not easy. What we have to assume next is that this is purely in terms of x. You guys can kind of see how where there's a problem, you just assume something to make the problem go away. Here, this is a problem. In general, it's not easy to solve, but we're going to assume this, and it just makes it solvable. Next, you assume this to be all in terms of x. So everything on the left side is in terms of x, everything on the right side is in terms of u. And let me just kind of flip this differential equation. So du over u dm dy, and if this is indeed all in terms of x, then you have something that's separated. All the x's on the right side, all the u's on the left side, and you get natural log of u is equal to this integral. And so u is simply this. And it's all divided by n. And that's how we're going to retrieve back our x. Case 2, and I'll let you guys show this yourself. If you assume u of x, y to just be simply in terms of y, you get u is the integral e to the integral of, and this is, I'm going to cheat, I'm going to look in the book. But it's exactly just this. But it's dn dx minus dm dy over your m, and then you hope all of these is just in terms of y, so you can integrate with respect to y. So u will be a function in terms of y. Okay. But for our first example, this example, our u is going to be in terms of x. Okay. All right. So let's go back to this problem and try to start with this, which is not exact, and retrieve back that x that we canceled out. So it's not exact, but you hope there exists a u of x or a u of y. You don't hope that it's both in terms of u, x, y, or else it's really hard, right? Okay, so how do we figure out if it's either u of x or u of y? You check the condition of both. So you'll see that you first want to check this. If it's just purely in terms of x. If it is, you can integrate with respect to x, and then your u is u of x. So you just have to check both. I'm just going to check this because I know it's going to be in terms of x, because I already know the factor that I cancel out is x, right? Because we're solving this problem which we know the solution to. Okay, so here's my m, here's my n. What is my dm dy? Well, it's going to be 3x plus 2e to the y. What is my dn dx? It's going to be 2x plus, and if I differentiate this with respect to x, you just get e to the y. And what is my n? It's x squared plus x e to the y. So I'm going to plug that right in. So this is 3x plus 2e to the y minus 2x plus e to the y, and you're subtracting the whole thing, so, and then divided by x squared plus x e to the y. And you hope this guy is all in terms of x, so I can integrate with respect to x. Okay, 3x minus 2x is an x. 2ey minus e to y is e to the y. And what do you notice? The bottom also contains a factor of x plus e to the y, if you factor out that x. There it is. It's just 1 over x. So this is e to the natural log of x. Cancel that out. You get just x. And you know, there is a plus c with a constant in front, but we can make the argument that once you plug it back in, that constant would just cancel out. So you can think of this u of x as just simply x, okay? Oh, sorry, you guys didn't see that. So yeah, there's a plus c and there's a constant in front. You can do this if you want. That a is not important, so you don't really have to worry about that a. So there it is. And I think I can just stop here because you guys know very well that if I multiply everything by x now, it is going to be exact, and then you continue the process. So now I know my u of x is x. Multiply by x, you get 3x squared y plus 2x e to the y, x to the third plus x squared e to the y. It's exact. Now we're back to section 2.4. 2.5 teaches us the method on how to undo this cancellation of that common factor. But of course, we're very dependent on the fact that we're canceling out a factor that is purely in terms of x or y. Okay, so that's 2.4 and 2.5. I'll see you guys in the next video.